Right now, light is racing past you at 670 million miles per hour. Every physicist on Earth agrees on that number. It is measured, confirmed, absolute. But here is a question that has quietly haunted internet forums, university lecture halls, and late-night conversations for decades. If light has a speed, does darkness have one too? When you flip a light switch off, does the darkness rush in at some measurable velocity? Does it travel faster than light, slower, or something else entirely? The answer dismantles one of the deepest intuitions humans carry about reality. It reveals that something you experience every single night does not actually exist the way your brain tells you it does. And it exposes a truth about the universe so fundamental that it governs everything from communication to time itself. If you enjoy having your understanding of reality completely rebuilt from the ground up, consider tapping that like button and subscribing. Now, settle in and get yourself comfortable. Let's begin. Somewhere inside the sun right now, something violent is happening. 600 million tons of hydrogen are being crushed together every single second, under pressures so extreme that the atoms themselves break apart. Protons that would normally repel each other with ferocious electromagnetic force are shoved so close together that the strong nuclear force takes over, fusing them into helium nuclei and releasing a small but staggering fraction of their mass as pure energy. 4 million tons of matter vanish every second, converted directly into radiation according to the most famous equation ever written. Energy equals mass times the speed of light squared. That equation is not a metaphor. It is a recipe. The sun is following it right now as you read these words, annihilating millions of tons of itself to keep burning. The energy produced in the core begins as gamma radiation, photons of such extreme frequency that they would obliterate any biological structure they touched. But these photons do not escape easily. The sun's interior is so dense, so packed with charged particles, that each photon travels only a fraction of a centimeter before colliding with an atom and being absorbed, re-emitted, scattered in a random direction. This process repeats trillions upon trillions of times. The photon takes a random walk through the solar interior, bouncing endlessly through a maze of plasma that stretches nearly 432,000 miles from center to surface. How long does this random walk take? Current estimates range from 10,000 to 170,000 years. A photon born in the core today will not see the surface until long after human civilizations have risen and fallen many times over. But the instant that photon breaks free of the sun's outer atmosphere, something extraordinary happens. It accelerates to its full and only speed. Not gradually, not over time, not through some build-up of velocity. Instantaneously. From the tangled prison of the solar interior to the vacuum of open space, the photon hits its terminal velocity in 0 seconds flat. 186,282 miles per second, 670 million miles per hour, the fastest speed anything in this universe will ever achieve. And here is what makes that number so strange. The photon did not choose that speed. It did not work up to it. That speed is the only speed it is capable of traveling in a vacuum. A photon cannot move slower through empty space. It cannot move faster. It exists at precisely that velocity from the instant of its creation to the instant of its destruction. There is no acceleration phase, no cruising altitude, no deceleration on approach. Light has one gear and one gear only, and it is the fastest gear the universe allows. This speed, designated by the letter c, is approximately 299,792 kilometers per second. It is measured with such extraordinary precision that scientists no longer treat it as a measurement at all. Since 1983, the speed of light has been a defined constant, and the meter itself is derived from it. 1 meter is the distance light travels in 1,299,792,458th of a second. We do not measure c anymore. We define our units of length by it. That is how foundational this number is. The measuring stick of human civilization is built on the back of a photon. But humanity did not always know light had a speed. For most of recorded history, the fastest thing anyone had ever experienced was a galloping horse or a released arrow. Light appeared wherever it was needed with no delay whatsoever. You open your eyes, the world is there. You strike a flint, the spark illuminates instantly. There was no reason to suspect light took time to travel from one place to another. The ancient Greeks debated the nature of vision extensively, but the idea that light might have a finite travel time was mostly dismissed. Empedocles suggested it in the 5th century BCE, but Aristotle rejected the idea, and Aristotle's word carried authority for nearly 2 millennia. The first real experiment came in 1638, when Galileo Galilei attempted to measure the speed of light using lanterns on distant hilltops. He stationed an assistant on a hill roughly 1 mile away. Galileo uncovered his lantern, and the assistant was supposed to uncover his the moment he saw Galileo's light. Galileo would then measure the delay between uncovering his own lantern and seeing the return flash. The experiment failed completely. The delay was imperceptible. Light crossed 2 miles so fast that human reaction times swamped any possible measurement. Galileo concluded that light was either instantaneous or extraordinarily fast. He was right about the second possibility. The breakthrough came 38 years later from an unexpected direction. In 1676, a Danish astronomer named Ole Rømer was working at the Paris Observatory, carefully timing the eclipses of Io, one of Jupiter's 4 large moons. Io orbits Jupiter roughly once every 42.5 hours, ducking behind the giant planet and re-emerging on the other side with clockwork regularity. Rømer had been logging these eclipses for months, building up a precise table of predicted times. But the predictions kept drifting. When Earth and Jupiter were relatively close together in their orbits around the Sun, the eclipses arrived a few minutes early compared to the predictions. When Earth was on the far side of its orbit, farther from Jupiter, the eclipses arrived late. The pattern was systematic and consistent, and Rømer realized it could not be explained by any irregularity in Io's orbit. What was changing was not Io's behavior, but the distance the light had to travel. When Earth was closer to Jupiter, light from the eclipse had a shorter path and arrived sooner. When Earth was farther away, the light needed more time to cross the additional distance. The eclipses themselves were perfectly regular. The information about them, carried by photons across interplanetary space, arrived early or late depending on the gap between the 2 planets. Rømer calculated that light took approximately 22 minutes to cross the diameter of Earth's orbit around the Sun. His estimate was rough by modern standards. The actual crossing time is closer to 16 minutes and 40 seconds, but precision was not the point. Rømer had established something revolutionary. Light travelled at a finite speed. It was not instantaneous. It took measurable time to get from one place to another. The universe did not communicate instantly. It communicated at a specific, limited rate. This discovery echoed through the following centuries, as physicists developed increasingly clever methods to pin down the exact value. In 1849, the French physicist Hippolyte Fizeau devised an ingenious apparatus. He directed a beam of light through the gap between teeth on a rapidly spinning cogwheel, aimed it at a mirror positioned roughly 8.5 kilometers away, and caught the reflected light as it returned through the next gap in the spinning wheel. By adjusting the wheel's rotation speed until the returning light passed perfectly through the adjacent gap, Fizeau could calculate how long the round trip had taken. His result was approximately 313,000 kilometers per second, about 5% above the modern value. Imperfect but astonishing for a tabletop experiment measuring the fastest phenomenon in nature. Léon Foucault refined the technique using rotating mirrors instead of cogwheels, achieving better precision. In the late 1800s and early 1900s, Albert Michelson dedicated decades to perfecting the measurement, eventually using mile-long evacuated tubes and precisely machined optical instruments to achieve values within a few kilometers per second of the modern constant. By the mid-20th century, laser interferometry and atomic clocks pushed the measurement to extraordinary precision, with uncertainties measured in fractions of a meter per second. Each refinement confirmed the same number. Light travelled at approximately 299,792.45 kilometers per second. The measurement was so consistent across so many independent methods that the scientific community took the radical step of defining units of length by it. The meter ceased to be an independent standard. It became a derivative of the speed of light. This was not merely a bureaucratic decision. It was a statement of profound physical confidence. Scientists trusted the constancy of c more than they trusted any physical artifact or measurement technique. The speed of light had become the bedrock, but measuring how fast light travels tells only half the story. The deeper question, the one that took centuries longer to answer, is what light actually is. And the answer turns out to be far stranger than a simple fast-moving projectile. For much of history, light was considered a stream of tiny particles. Isaac Newton championed this corpuscular theory in the late 1600s, arguing that light consisted of minute bodies emitted by luminous objects. The theory explained reflection neatly, particles bouncing off surfaces like tennis balls off a wall. But it struggled with other phenomena, particularly the patterns of bright and dark bands that appeared when light passed through narrow slits or around sharp edges. These interference and diffraction patterns look suspiciously like the behavior of waves, not particles. In the early 1800s, Thomas Young's double-slit experiment provided compelling evidence that light was a wave. When coherent light passed through two closely spaced slits, it produced an interference pattern on a distant screen, alternating bands of brightness and darkness. This pattern could only be explained if light waves from the two slits were overlapping, reinforcing each other where crests met crests and cancelling where crests met troughs. Particles could not produce this pattern. Waves could. The wave theory triumphed for most of the 19th century, but a troubling question lingered. Waves need a medium. Sound waves require air or another material to propagate. Water waves require water. What medium did light waves travel through? Scientists hypothesized a substance called the luminiferous ether, an invisible, massless material filling all of space through which light waves oscillated. The ether was supposed to be rigid enough to support extremely high-frequency vibrations, yet tenuous enough to offer no resistance to the motion of planets. In 1887, Albert Michelson and Edward Morley designed what should have been the definitive test. If the ether existed, and Earth moved through it in its orbit around the Sun, then light travelling in the direction of Earth's motion should move at a slightly different speed than light travelling perpendicular to it, much like swimming with or against a river current. Using an interferometer of extraordinary precision, Michelson and Morley looked for this speed difference. They found nothing. No matter what direction they measured, light travelled at the same speed. The ether, if it existed, had no detectable effect on light's velocity. The null result baffled physicists. Some proposed that the ether was dragged along by Earth's motion. Others suggested the apparatus contracted in the direction of motion, perfectly cancelling the expected signal. But the simplest explanation, the one that eventually prevailed, was that the ether did not exist. Light did not need a medium. It propagated through empty space entirely on its own. The theoretical framework that made sense of this had actually been developed 2 decades before Michelson and Morley ran their experiment. In the 1860s, the Scottish physicist James Clerk Maxwell unified electricity and magnetism into a single coherent theory described by 4 elegant equations. These equations described how electric charges produce electric fields, how moving charges produce magnetic fields, how changing magnetic fields produce electric fields, and how changing electric fields produce magnetic fields. The 4 equations interlocked, each feeding into the others. When Maxwell solved his equations for empty space, with no charges or currents present, something remarkable fell out. The equations predicted the existence of self-sustaining waves of oscillating electric and magnetic fields, propagating through the vacuum at a speed determined entirely by two fundamental constants: the electric permittivity of free space and the magnetic permeability of free space. These two constants describe how strongly the vacuum responds to electric and magnetic fields respectively. Multiply them together, take the inverse, and take the square root. The result is a speed. Maxwell calculated that speed and found it matched the measured speed of light almost exactly. The implication was staggering. Light was an electromagnetic wave, not a separate phenomenon requiring its own explanation. An electromagnetic wave, identical in nature to the radio waves, microwaves, infrared radiation, ultraviolet rays, X-rays, and gamma rays that would later be discovered across the full electromagnetic spectrum. All of these phenomena were oscillating electric and magnetic fields propagating through space at the same fundamental speed. They differed only in wavelength and frequency. Visible light occupied a narrow band in the middle of an enormous spectrum. This meant the speed of light was not some arbitrary cosmic speed limit plucked from thin air. It emerged directly from the properties of empty space itself. The vacuum has a specific electric permittivity and a specific magnetic permeability, and the combination of these two properties determines exactly how fast electromagnetic disturbances can propagate. The speed of light is baked into the fabric of space. It is not a speed that light happens to achieve, it is the speed that the structure of the vacuum demands. Then came the revolution that shattered any remaining simplicity. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would dismantle 3 centuries of assumptions about space and time. Albert Einstein did not discover that the speed of light was constant. Maxwell's equations already implied it. What Einstein did was take that constancy with absolute seriousness and follow it wherever it led, no matter how bizarre the consequences. Einstein's starting point was simple. The laws of physics should look the same to all observers moving at constant velocities relative to each other, and the speed of light in a vacuum should be the same for all such observers, regardless of how fast they are moving or in what direction. These two postulates sound modest. Their consequences were catastrophic for classical physics. If the speed of light is the same for everyone, then something else must give when observers move relative to each other. That something turned out to be space and time. Distances contract in the direction of motion. Clocks tick slower for moving observers. Events that appear simultaneous to one observer occur at different times for another observer in motion. Mass increases as velocity increases, requiring ever more energy to accelerate further, and at the speed of light itself, the equations break down entirely. A massive object approaching c would require infinite energy to reach it. The speed of light is not merely a practical barrier, it is a structural wall in the mathematics of reality. But Einstein's framework revealed something even more profound than a cosmic speed limit. It revealed what that speed limit actually governs. The speed of light is not merely the speed at which photons happen to travel. It is the maximum speed at which any causal influence can propagate through spacetime. No force, no signal, no interaction of any kind can outrun c. Gravity propagates at the speed of light. Changes in electromagnetic fields propagate at the speed of light. Even the nuclear forces that bind protons and neutrons inside atomic nuclei operate within a framework where c is the absolute ceiling. If you disturb something here, the earliest that disturbance can affect something over there is the time it takes light to travel the distance between them. This is not an engineering limitation. It is not that our technology lacks the power to send signals faster. The universe itself does not transmit causal connections faster than c. If you try to write down the equations for a signal traveling faster than light, you get results that violate causality. Effects precede causes. Messages arrive before they are sent. Logical paradoxes emerge that are not merely confusing, but physically incoherent. The speed of light is the universe's mechanism for keeping events in order, for ensuring that causes always precede their effects. This makes photons even more remarkable than their raw speed suggests. Photons are massless particles. In the framework of special relativity, Massless particles do not merely happen to travel at sea. They must travel at sea. They have no choice. A photon cannot slow down in a vacuum any more than you can stand still on a treadmill, moving at infinite speed. The instant a photon is created, whether in the core of a star, the filament of a light bulb, or the antenna of a radio tower, it is moving at the speed of light. The instant it is absorbed by an atom, a retina, or a solar panel, it ceases to exist. Between creation and destruction, it exists in a state of perpetual motion at exactly c, no more, no less, not ever. From the photon's own perspective, to the extent that such a concept even applies, something even more bewildering occurs. Special relativity predicts that, as an observer approaches the speed of light, time dilates. Clocks tick slower. Events that take years in a stationary frame compress into moments. At exactly c, time dilation becomes infinite. Time stops entirely. A photon emitted from a star 26,000 light-years away experiences no elapsed time during its journey. From its frame of reference, emission and absorption are the same event. The photon's entire existence, its creation inside a stellar furnace and its death against your retina on a dark night, happens in a single instant of its own non-existent clock. It crosses the galaxy in 0 seconds of its own time. We are not dealing with an ordinary phenomenon. Light is a massless quantum of electromagnetic energy that exists at one and only one speed, determined by the fundamental properties of the vacuum, carrying energy and information across space-time at the maximum rate the universe permits. It has measurable properties: wavelength, frequency, energy, momentum, polarization, spin. It interacts with matter in well-understood ways, reflecting, refracting, diffracting, being absorbed and re-emitted by atoms. It has been counted individual photon by individual photon in laboratory experiments. It is real, physical, and extraordinarily well characterized. The speed of light has been measured by eclipses of moons, spinning cogwheels, rotating mirrors, laser interferometers, and atomic clocks. It has been confirmed by the motion of stars, the timing of spacecraft communications, the behavior of particle accelerators, and the precise predictions of quantum electrodynamics. Every measurement, across every method, across every decade, converges on the same number: 299,792.458 kilometers per second. It is one of the most precisely known quantities in all of science. So here we stand with an extraordinarily detailed understanding of light. We know what it is made of, we know how it propagates, we know its exact speed, we know why that speed takes the specific value it does, we know what role it plays in the structure of space-time and the enforcement of causality. We know more about the physics of light than perhaps any other phenomenon in the natural world. And this brings us to a question that sounds childishly simple, but conceals a depth that catches even scientifically literate people off guard. If we know all of this about light, what can we say about its opposite? What about darkness? When you switch off a lamp and the room goes black, what exactly happened? Did something leave? Did something arrive? Is the darkness that now fills the room a thing, a substance, an entity with its own physical identity? Does it have a speed? Did it rush in from the corners, flood through the doorway, descend from the ceiling? Or did something else happen entirely? Something that challenges the way your brain has processed the experience of light and dark since the day you were born? The answer begins with a distinction so fundamental that it reshapes how you understand not just optics, but the nature of physical reality itself. It is the difference between something and nothing, between a presence and an absence, between an entity that physics can describe and a concept that exists only in the human mind. And once you grasp that distinction clearly, everything you thought you knew about darkness begins to unravel. Stand in a concert hall as a full orchestra performs the final crashing chord of a symphony. Sound waves radiate from every instrument simultaneously. pressure fronts rippling through the air at roughly 760 miles per hour, colliding and interfering with each other in complex patterns that your eardrums translate into something magnificent. The sound is real. It has frequency, amplitude, wavelength. It carries energy. It exerts measurable pressure on the surfaces it strikes. You can record it on tape, encode it in digital ones and zeros, broadcast it across the planet through satellite signals. Sound is a physical phenomenon with properties you can quantify, predict, and manipulate. Now the conductor lowers the baton. The musicians lift their bows from the strings. The brass players pull the mouthpieces from their lips. The final chord decays into nothing. Silence. Here is the question that contains the seed of everything that follows. Did silence arrive? Did a wave of quiet radiate from the stage at some measurable speed, sweeping across the concert hall row by row until it reached the back wall? Is silence a thing that travelled to your ears? The answer is so obvious it barely seems worth stating. No. Silence did not travel anywhere. Silence has no speed, no frequency, no wavelength, no energy. Nothing radiated from the stage. The musicians simply stopped producing sound waves, and the existing waves dissipated through absorption by walls, seats, clothing, and air molecules. What remained was the absence of organized pressure fluctuations. The air was still there, molecules were still bouncing around at thermal velocities, but the coherent vibrations that constitute sound had ceased. Silence is the word we use for that cessation. It is a description of a condition, not a description of a substance. Nobody struggles with this concept when it comes to sound. Nobody asks what the speed of silence is. Nobody wonders whether silence is made of anti-sound particles. Nobody imagines that when a room goes quiet, some mysterious substance floods in through the walls to fill the void left behind by the departing noise. The idea is absurd on its face. Silence is obviously nothing. It is the absence of something. Darkness is identical. In every single physical respect, darkness is to light what silence is to sound. It is not a substance. It is not a particle. It is not a wave. It is not a field. It is not a force. It carries no energy. It exerts no pressure. It has no wavelength, no frequency, no momentum, no spin, no polarization. It does not propagate through space. It does not interact with matter. It does not exist as an entry in any catalogue of physical entities ever compiled by any physicist in the history of the discipline. Darkness is a word, a human invention, a label applied to the condition of insufficient photons in a region of space to stimulate visual perception or electromagnetic detection. That is all it is, a deficit, an absence, a nothing with a name. The standard model of particle physics, the most successful scientific theory ever constructed, accounts for every known fundamental particle and every known fundamental force. It describes quarks, leptons, gauge bosons, and the Higgs boson. It catalogues the photon, the gluon, the W and Z bosons. It includes neutrinos in 3 flavors, 6 types of quarks, and their corresponding antiparticles. It does not include a darkness particle. There is no darkon, no shadow boson, no antiphoton that constitutes the substance of darkness. If darkness were a physical entity, it would need to appear somewhere in this framework. It does not. Its absence from the catalogue is not an oversight. It is a reflection of the fact that there is nothing to catalogue. This seems straightforward enough when stated plainly. Yet something about the human experience of darkness resists this clean categorization. Darkness feels like a presence. Walk into a pitch-black room and your body responds as though something tangible surrounds you. Your pupils dilate, straining to collect photons that are not there. Your skin prickles. Your heartbeat may quicken. Your brain shifts into a heightened state of alertness, processing auditory and tactile information with increased sensitivity to compensate for the lost visual channel. The emotional weight of darkness is real, even if darkness itself is not a thing. This perceptual bias runs deep. It is embedded in human language, mythology, and storytelling at the most fundamental levels. Darkness falls, shadows creep, night descends, gloom gathers. Every one of these phrases treats darkness as an active agent, a substance that does things in the world, that moves, that acts, that arrives. Ancient civilizations built entire theological systems around the opposition between light and dark, treating them as equal and opposite cosmic forces locked in eternal struggle. The Zoroastrians framed existence as a battle between Ahura Mazda, the Lord of Light, and Angra Mainyu, the Lord of Darkness. Egyptian mythology centered on the sun god Ra's nightly journey through the underworld of dark. Norse cosmology began in the void of Ginnungagap, a primordial darkness preceding creation. These mythologies feel intuitively correct because human experience presents light and dark as symmetric opposites. Day and night alternate with the rotation of the Earth. Illuminated spaces and shadowed spaces coexist in every landscape. Light and dark appear to fill rooms in equal measure, one replacing the other in a rhythmic exchange that seems perfectly balanced. Your brain processes both states as positive experiences, as things you perceive, rather than processing one as a thing and the other as the absence of that thing. But physics does not care about human intuition. Physics describes what exists and how it behaves, and physics is unambiguous on this point. The symmetry between light and dark is an illusion manufactured by the human visual system. Light is a physical phenomenon with measurable properties. Darkness is a perceptual state corresponding to the absence of that phenomenon. They are not two substances occupying a room in alternation. They are a substance, and the lack of that substance. The relationship is fundamentally asymmetric. Consider the properties you can assign to light: wavelength, frequency, energy, momentum, polarization, speed, direction of propagation, spin, angular momentum. Every one of these properties is measurable, quantifiable, and governed by precise equations. You can calculate the energy of a photon from its frequency using Planck's constant. You can predict its momentum from its wavelength. You can determine its speed from the permittivity and permeability of the medium it travels through. You can describe its polarization as linear, circular, or elliptical. Light has a rich, detailed physical identity. Now try assigning properties to darkness. What is the wavelength of darkness? There is no answer because wavelength describes an oscillation, and darkness does not oscillate. What is the energy of darkness? Zero, or rather, the question does not apply because darkness is not an entity that carries energy. What is the momentum of darkness? Same problem. What is the polarization of darkness? The concept does not translate. What is the frequency of darkness? There is nothing to have a frequency. Every property you attempt to assign to darkness turns out to be either zero or undefined. This is not because darkness is some exotic phenomenon that physics has not yet learned to characterize. It is because darkness is not a phenomenon at all. It is the descriptor we apply when the phenomenon of light is absent. Trying to assign physical properties to darkness is a category error of the most fundamental kind. It is like asking how much a vacuum weighs, or what shape Wednesday is, or how loud emptiness can get. The question applies a concept to a category where the concept has no meaning. The question applies a concept to a category where the concept has no meaning. A useful parallel comes from thermodynamics. Heat is a form of energy. Specifically, it is the transfer of thermal energy between systems at different temperatures, driven by molecular kinetic energy. When molecules move faster, a substance is hotter. When they move slower, it is cooler. Heat can be measured in joules, quantified precisely, and tracked as it flows from hot objects to cooler surroundings. It obeys the laws of thermodynamics. It radiates, conducts, and convects through materials in well-understood ways. Heat is a physical phenomenon. Cold is not. There is no particle of cold. No coldness field permeates space. When something cools down, it is not because a substance called cold arrived and displaced the heat. It is because heat energy left the object, transferring to the surroundings through radiation, conduction, or convection. The object contains less thermal energy than before, and we describe its new state as cold. But cold is not a thing, it is a condition, a description of reduced energy, a word for what remains when heat is absent. Physicists spent centuries being confused about exactly this distinction. Before the development of thermodynamics, a theory called caloric proposed that heat was an invisible fluid that flowed between objects. Hot objects contained a lot of caloric fluid. Cold objects contained little. Heating something meant adding caloric. Cooling meant removing it. The theory was elegant, intuitive, and wrong. Heat turned out not to be a substance at all, but a process, a transfer of kinetic energy between particles. The caloric model was a category error that treated a process as a thing. Darkness invites the same category error. Human intuition wants to treat it as a substance, a thing that fills space, a counterpart to light. The urge is understandable. Darkness occupies space in your visual field. It surrounds objects. It seems to have depth and texture. But all of these impressions are artifacts of how your brain processes the absence of visual information. The depth you perceive in darkness is your visual cortex interpolating over a region where it has no data. The texture is noise in your retinal signal amplified by a brain desperate for patterns. Darkness is your brain's screensaver, not a feature of external reality. With this foundation in place, we can now trace exactly what happens at the physical level when a light source turns off. Understanding this sequence of events dissolves the question of darkness having a speed more thoroughly than any abstract argument. Consider a simple scenario. A single lamp sits in the center of a room that is 5 meters across. The lamp emits photons in all directions. These photons travel outward at the speed of light and reach the nearest wall in approximately 16 nanoseconds, 16 billionths of a second, so fast that to any human observer, the room appears to fill with light the instant the lamp switches on. The walls, ceiling and floor reflect some fraction of these photons, which bounce around the room in complex patterns, scattering off surfaces until they are eventually absorbed. At any given moment, the room contains a large population of photons in transit between surfaces, and the steady stream of new photons from the lamp maintains this population at a constant level. The room is bright. Now switch the lamp off. The filament or diode ceases emitting photons. This is the only event that occurs. A source stops producing particles. No new substance is created. No signal is broadcast. No dark energy is released. A process ends. That is all. But the photons already in flight do not know the source has stopped. They continue traveling at sea, striking walls and being absorbed or reflected. The last photon emitted by the lamp before shutdown travels outward and hits the nearest surface 16 nanoseconds later. Any photons still bouncing between walls complete their final reflections and are absorbed within a few tens of nanoseconds after that. Within perhaps 50 to 100 nanoseconds, every photon in the room has been absorbed. No new photons replace them. The room is dark. What happened during those final nanoseconds? Light left. That is the entire story. Photons completed their journeys and were absorbed. No replacement photons arrived. The room transitioned from a state of photon abundance to a state of photon absence. Nothing entered the room to make it dark. Something stopped entering the room, and the darkness was what remained. The speed at which the room becomes dark is determined entirely by how fast the last photons clear the space. That speed is c, not because darkness moves at c, but because the photons, whose departure defines the darkness, move at c. The darkness itself has no velocity. It is the aftermath, not the agent. Attributing speed to the darkness would be like attributing speed to the silence that follows a gunshot. The silence does not travel outward from the gun. The sound does. When the sound passes, silence is what remains at each point it leaves behind. Now, stretch this thought experiment to a scale where the distinction becomes even more vivid. Imagine a star burning, steadily 10 light-years from Earth. For billions of years, this star has been emitting photons in all directions, and a tiny fraction of those photons have been travelling toward our planet, arriving as a faint point of light in the night sky. The stream of photons is continuous. At any given moment, photons from this star occupy every point along the 10 light-year path between the star and Earth, each one moving toward us at c, each one carrying information about the star's luminous state. Now suppose this star instantaneously stops shining. Perhaps it undergoes a catastrophic collapse. Perhaps some hypothetical mechanism simply shuts off its nuclear furnace in a single instant. At the moment the star goes dark, the situation along the 10 light-year path is this. An unbroken column of photons stretches from the star's former position to Earth, each photon moving toward us at c. The photon at the very front of this column, the one closest to Earth, will arrive first. The photon at the very back, the last one emitted before shutdown, sits right next to the now dark star. From Earth's perspective, nothing changes. The star continues to shine exactly as it did before, because the photons, already in transit, keep arriving on schedule. 1 year after the star went dark, photons emitted 1 year before shutdown are arriving at Earth. 5 years after, photons from 5 years before shutdown are reaching us. The star appears perfectly normal. There is absolutely no indication that anything has changed. 10 years after the star went dark, the last photon in the column arrives at Earth. It is the final photon the star ever emitted, the one that was sitting right at the star's surface when the shutdown occurred. That photon strikes the detector, and then nothing follows it. No more photons arrive from that direction. The star vanishes from the sky. Did darkness travel from the star to Earth over 10 years? This is the critical question, and the answer illuminates the entire concept. No. Nothing travelled from the star to Earth except photons. The photons travelled at c. They carried information about the star's state at the moment of their emission. The last photon carried the last piece of information. The star was still shining when this photon left. After it arrived, there was no further information to carry. The star was gone. No more photons were coming. The direction in the sky where the star used to be became dark. But that darkness is not a thing that crossed 10 light years of space. It is the end of a stream, the absence of continuation. Think of a faucet. Turn it on, and water flows into your sink. Turn it off, and the water already in the pipe drains out. Then the flow stops. Did dryness travel through the pipe from the valve to the faucet? No. Water travelled through the pipe. When the water stopped, dryness was what remained. Dryness did not flow. Water flowed, then it stopped flowing. The same logic applies at every scale. Whether the light source is a lamp 5 meters away or a quasar 5 billion light years away, the physics is identical. When a source stops emitting, the final photons travel outward at c, and behind them trails a region of photon absence. That region of absence expands at c, but only because the photons at its leading edge are travelling at c. The absence itself is not a thing that expands. It is the wake left behind by the departure of the last light. This leads to a statement that sounds almost paradoxically simple given the complexity of the question that motivated it. Darkness does not have a speed, because darkness does not travel. It does not travel because it is not a thing. It is not a thing because it has no physical properties, no mass, no energy, no momentum, no wavelength. It is a condition described by the absence of photons. The transition from light to dark at any given point is caused by events at the light source, and the information about those events propagates to the observation point at the speed of light, carried by the last photons to make the journey. The reason this simple truth is so hard to absorb is that human cognition is fundamentally biased toward treating absences as presences. Psychologists call this reification, the tendency to treat abstract concepts as concrete things. We reify darkness constantly. We speak of it as though it has agency. We imagine it spreading, flowing, advancing, retreating. We treat it as the opponent of light, rather than as the default state that exists when light is absent. This bias is not a flaw. It was enormously useful for survival. Organisms that treated darkness as a potential threat survived at higher rates than those that dismissed it as a neutral absence. Our brains are built to take darkness seriously, which means treating it as substantive and real, even when physics says otherwise. But physics operates on a different standard than evolutionary survival. Physics asks not what is useful to believe, but what is actually true. And the truth is that darkness has no physical existence independent of the light whose absence defines it. Every question you can ask about darkness reduces to a question about light. How dark is this room? That is a question about how many photons per second are arriving at a detector. How fast does darkness spread? That is a question about how fast the last photons clear a space. Where is the boundary between light and dark? That is a question about the spatial distribution of photon intensity. You cannot ask a single meaningful question about darkness that does not ultimately resolve into a question about photons. The concept of darkness provides no additional explanatory power beyond what the concept of light already delivers. In the language of physics, darkness is not an independent degree of freedom. It is not a separate variable in any equation. It adds nothing to the mathematical description of reality. This might feel like a diminishment. Darkness is one of the most evocative concepts in human experience. It shapes art, literature, religion, psychology. It is central to the human experience of fear, mystery, awe, and beauty. Stripping it of physical reality might seem to rob it of significance. But the opposite is true. Understanding what darkness actually is, understanding that every dark space in the universe is simply a region where the most remarkable physical phenomenon we know of is absent, deepens the appreciation of both light and its absence. Every photon is a messenger, a quantum of energy traveling at the maximum allowed speed of the cosmos, carrying information from one point in spacetime to another. Every dark region is a place those messengers have not reached, or have reached and departed, or are being prevented from reaching. The darkness between galaxies is not a substance separating them. It is an absence of photons in the vast spaces where no stars shine brightly enough to fill the void. But if darkness is truly nothing, if it has no speed, no substance, no physical identity, then how do we explain something that physicists themselves have confirmed? There are situations where shadows, those most familiar manifestations of darkness, appear to move across surfaces faster than the speed of light. This is not a theoretical possibility. It is a geometric certainty, and when you first encounter the mathematics behind it, it seems to shatter everything we have established about what darkness cannot do. The resolution of this apparent contradiction turns out to be one of the most illuminating lessons in all of physics. It does not rescue the idea that darkness has a speed. It does something far more interesting. It reveals what the speed of light actually prohibits and what it permits in a universe where the line between reality and illusion is drawn by the principle of causality. In the early 1970s, a team of radio astronomers pointed their instruments at a distant object called 3C 279, a quasar burning with the intensity of 1 trillion suns roughly 5 billion light-years from Earth. Over months of observation, they tracked a blob of radio-emitting plasma that appeared to be moving away from the quasar's core. When they calculated the apparent speed of this blob across the sky, the number that fell out of their equations was disturbing. The plasma appeared to be moving at more than 4 times the speed of light. The discovery ignited a firestorm in the astrophysics community. Einstein's special relativity, confirmed by half a century of experiments, declared that nothing carrying mass or energy could exceed c. Yet here was a blob of hot plasma, very much a physical object with mass and energy, apparently cruising through space at 4c. Had relativity been broken? Had astrophysicists discovered a loophole in the fundamental laws of the universe? They had not. What they had discovered was one of the most elegant geometric illusions in nature, a phenomenon called superluminal apparent motion. The plasma was not actually moving faster than light. It was moving very close to light speed, roughly 98% of C aimed nearly directly toward Earth. This specific combination of high real velocity and small angle to the line of sight created a projection effect that made the transverse motion appear enormously amplified. Here is how the geometry works. Imagine the quasar jet shooting a blob of plasma at 98% of C, aimed just 5 degrees away from pointing directly at Earth. The blob moves along its true trajectory through space, but because it is moving almost directly toward us, the light it emits at the beginning of its journey and the light it emits later in its journey travel nearly the same path to reach us. The light emitted later has a much shorter distance to cover, because the blob has moved substantially closer to Earth in the meantime. This means the two light signals arrive at Earth separated by a much smaller time interval than the actual time that elapsed between emissions. The blob appears to have crossed the angular distance on the sky in a compressed time frame, making its apparent transverse speed much larger than its true speed. The specific trigonometry produces a maximum apparent velocity of roughly the true speed multiplied by the Lorentz factor, which at 98% of C is about 5. Hence, the quasar blob appeared to move at 4 to 5 times light speed while actually travelling below C the entire time. The key insight was this: the plasma blob was real. It carried mass and energy. It moved through space at a genuine velocity below C. But its apparent motion across the sky, as perceived by distant observers, exceeded C due to the geometry of the observation. The appearance of superluminal speed was not a property of the object. It was a property of the observation, and this distinction between what physically happens and what appears to happen turns out to be the central idea needed to understand how shadows can seem to outrun light. Consider the simplest possible scenario. You are standing in a field on a dark night holding a powerful flashlight. 50 meters in front of you stands a long wall. You aim the flashlight at the left end of the wall and then sweep the beam rapidly to the right. The bright spot traces a path across the wall from left to right. If the wall is long enough and your sweep is fast enough, that bright spot can move across the wall at any speed you like. There is no upper limit. The speed of the spot is determined by the angular rate of your sweep multiplied by the distance to the wall, and you can make either of those quantities as large as you want. At 50 meters, a quick wrist flick might move the spot across the wall at a few hundred meters per second. Unremarkable. But now, imagine the wall is on the moon, 240,000 miles away. That same wrist flick sweeps the beam across a surface so distant that the projected spot must cover thousands of miles to keep up with the angular motion. A casual sweep of your wrist could move the spot across the lunar surface at speeds exceeding C by a comfortable margin. The dark region trailing behind the spot, the shadow that follows the bright dot as it races across the moon's face, moves at exactly the same superluminal apparent speed. Darkness, or at least something that looks exactly like moving darkness, appears to outrun the fastest thing in the universe. This is confirmed physics. It is not controversial. No serious physicist disputes that shadows and projected spots can exhibit apparent superluminal motion. The phenomenon follows directly from basic geometry and has been observed in multiple astrophysical contexts beyond the quasar jets that first brought it to scientific attention. The question is not whether it happens, but what it means. And what it means is something far more subtle and far more important than a simple violation of Einstein's speed limit. To understand why superluminal shadow motion violates nothing, you have to understand what the bright spot on the moon actually is at the physical level. Your laser pointer emits a continuous stream of photons. These photons leave the pointer, travel through space at C, and strike the lunar surface roughly 1.3 seconds later. When the beam is aimed at a specific point on the moon, photons arrive at that point and scatter in all directions, some of them bouncing back toward Earth where your eyes or a telescope can detect them. This creates the appearance of a bright dot at that location. Now you flick your wrist. The beam swings to a new angle. Photons emitted after the flick travel along the new trajectory, also at C, and arrive at a different point on the moon 1.3 seconds after emission. These new photons create the appearance of a bright dot at the new location. The old dot has disappeared because no more photons are arriving at the old location. The new dot has appeared because photons are now arriving at the new one. Here is the essential point. The photons that created the dot at position A are entirely different physical objects from the photons that created the dot at position B. No individual photon travelled from A to B along the lunar surface. Every single photon travelled from the laser pointer to the moon in a straight line at C. The dot at A was made by one set of photons. The dot at B was made by a completely different set. The apparent motion of the dot across the moon is not a physical object moving across a surface. It is a sequence of independent events, photon arrivals, occurring at different locations in rapid succession. The analogy that makes this clearest is a marquee sign. Picture those old theatre signs where rows of light bulbs switch on and off in sequence, creating the illusion of a bright region sweeping across the sign. Watch the pattern, and it appears to move smoothly from left to right, but nothing physical moves from left to right. Each bulb turns on independently in response to its own electrical signal. The bulb on the left has no causal connection to the bulb on the right through the apparent motion. They are connected only through the central controller that triggers them in sequence. The apparent motion is a pattern, an artifact of sequential timing, not a physical displacement. You could make the pattern sweep across the marquee at any speed whatsoever. Simply adjust the timing of the electrical signals. Make them fire in quicker succession, and the pattern moves faster. There is no speed limit on the pattern, because the pattern is not a physical object. No mass moves from left to right. No energy transfers from bulb to bulb along the horizontal direction. Each bulb receives its energy vertically from the electrical circuit beneath it. The horizontal motion is pure illusion. The dot on the moon works identically. Each point on the lunar surface receives its photons vertically, so to speak, from the laser beam travelling through space at C. The horizontal motion of the dot across the surface is pure projection. No energy travels horizontally along the moon's surface from point A to point B. No information passes between the 2 points through the moving dot. Each illuminated spot is independently connected to the source through its own set of photons, and each of those photon streams travels at exactly C. The shadow trailing behind the dot obeys the same logic with even greater clarity. When the bright dot moves from A to B, point A becomes dark because photons are no longer being directed there. This darkening at A is not caused by anything that happened at B. It is caused by the change in the laser pointer's angle back on Earth. The pointer stopped aiming at A, so photons stopped arriving at A. That causal chain runs from Earth to point A through space at C. The darkening at B a moment later, when the dot moves onward to point C, follows the same independent causal chain. The pointer changes angle, photons stop arriving at B, B goes dark. No causal signal travels along the moon's surface from A to B at superluminal speed. Each point on the surface receives its own independent instructions from the laser pointer through photons travelling at C. The shadow does not carry information from A to B, any more than the silence after a concert carries information from one end of the hall to the other. But why does this matter? Why do physicists care about this distinction between apparent motion and real motion? Because the speed of light is not actually a speed limit on motion in the colloquial sense. It is a speed limit on something more fundamental, the transmission of information. This is one of the most commonly misunderstood aspects of special relativity. The popular summary says, "Nothing can travel faster than light." But that phrasing is imprecise in a way that leads to exactly the confusion we are untangling here. The precise statement is that no causal signal can propagate faster than c. No information can be transmitted from one location to another at a speed exceeding light speed. No event at point A can influence an event at point B faster than a photon could travel from A to B. This is a restriction on causality, not on appearances. Patterns, projections, geometric intersection points, and phase velocities can all exceed c without any physical law being violated, precisely because none of these things transmit causal information between 2 points. The distinction becomes vivid with a concrete test. Imagine you wanted to use the moving dot on the moon to send a message faster than light. You station an observer named Clara at point A on the lunar surface, and another observer named Daniel at point B, 1,000 miles away. You want Clara to communicate a piece of information to Daniel faster than a light beam could cross the 1,000 miles between them. Light takes approximately 5.4 milliseconds to cover that distance. If the dot sweeps from A to B in less than 5.4 milliseconds, it has outpaced light. Can Clara use that dot to send Daniel a message? Here is what happens. Clara stands at point A. She sees the dot arrive. It illuminates her location briefly. Then it moves on toward B. Daniel, standing at point B, sees the dot arrive at his location a moment later. From the timing, the dot crossed the distance between them faster than light would have. But what did Daniel learn from the dot's arrival? He learned that the laser pointer back on Earth is now aimed at his position. That is all. The dot told him something about Earth, not something about Clara. He has no idea what Clara's doing, thinking, or trying to communicate. The dot at his location was not caused by anything that happened at Clara's location. It was caused by the pointer on Earth changing its angle. The causal chain runs from Earth to Daniel, not from Clara to Daniel. Suppose Clara wanted to encode a message in the dot. She might try to block the beam as it passes her position, creating a gap in the dot's sweep that Daniel could interpret as a signal. But this does not work either. If Clara blocks the beam at point A, the photons headed for her location are absorbed by her hand or her equipment. The photons heading for Daniel's location are already in flight from Earth, on a completely different trajectory. Clara's action at point A does not affect the photons arriving at point B, because those are different photons on different paths. The only way Clara could block Daniel's photons would be to physically intercept the beam between Earth and Daniel's position, which would require her to move into a completely different location. Clara could try to radio Daniel with the information, but radio waves travel at sea. She could try to flash a light at him, but light travels at sea. Every method Clara has for transmitting information to Daniel is bound by the speed of light. The superluminal dot sweeping between them offers no shortcut, no workaround, no cheat code. The dot's apparent speed is completely irrelevant to information transfer, because the dot is not the information carrier. The photons are, and each photon independently obeys the speed limit on its own straight-line path from Earth. This test, the inability to use superluminal apparent motion to transmit information faster than light, is the definitive criterion that separates real motion from apparent motion in physics. Any phenomenon that allows faster than light apparent motion but does not permit faster than light information transfer is physically permitted. Any phenomenon that would allow actual faster than light information transfer would violate causality and is physically forbidden. Shadows and projected dots fall squarely in the permitted category. They can appear to move at any speed because they do not carry information between the points they appear to cross. Each point receives its causal instructions in the form of arriving or non-arriving photons, independently from the source at the speed of light. This principle shows up in a real-world phenomenon that nearly every person on Earth has experienced without recognizing its superluminal nature: a solar eclipse. During a total solar eclipse, the moon passes between Earth and the sun, casting a shadow on our planet's surface. That shadow, the region of totality, races across the landscape at tremendous speed. Observers in its path experience a sudden plunge into darkness lasting a few minutes before sunlight returns. The shadow cone sweeps across the Earth following the geometry of the moon's orbital motion, combined with the Earth's rotation. The typical speed of an eclipse shadow across the Earth's surface ranges from roughly 1,000 to 5,000 miles per hour, well below the speed of light. But this is only because the moon is relatively close to Earth, about 240,000 miles away, and its angular velocity is modest. Now imagine a similar eclipse geometry, but with the occulting body much farther away and moving at a sharper angle. The shadow could sweep across a sufficiently distant surface at speeds approaching or exceeding c. In fact, Astrophysical eclipses and occultations in distant systems can produce exactly this effect. When a compact object transits across the face of a distant emission nebula, the shadow it casts on material behind it can sweep through space at apparent superluminal speeds, depending entirely on the geometry of the alignment. Each point in the nebula independently transitions between illuminated and shadowed states based on whether its own line of sight to the background source is currently blocked. The shadow carries no information laterally through the nebula from one point to the next. Each point's experience is determined by its own independent geometric relationship with the occulting object and the light source. Even our familiar terrestrial eclipse illustrates the principle. The shadow of totality racing across the countryside at thousands of miles per hour is not a physical object tearing through the atmosphere. It is a geometric projection, a region where photons from the sun are being blocked by the moon. Each point on the ground independently enters shadow when the moon moves between that specific point and the sun along that specific line of sight. Adjacent points enter shadow at slightly different times because their lines of sight to the sun are blocked at slightly different moments. The aggregate effect looks like a shadow sweeping smoothly across the surface, but nothing physical moves along that surface from one shadowed point to the next. This same principle shows up in numerous other physical contexts, and seeing it in multiple settings reinforces why the speed of light remains inviolate even when apparent superluminal motion abounds. Consider a pair of scissors, extremely long scissors, hundreds of thousands of miles in length. You close the blades rapidly near the handles. The point where the blades intersect, the cutting point, races outward along the length of the blades toward the tips. If the scissors are long enough, this intersection point can move faster than c. But no physical material travels from the handles to the tips at that speed. Each atom in each blade moves only a tiny distance at a speed far below c. The intersection point is a geometric relationship between two independently moving surfaces, not a physical object. It carries no information from handles to tips faster than the mechanical compression wave traveling through the blade material, and that wave propagates at the speed of sound in the metal, far below c. Or consider ocean waves approaching a long beach at a slight angle. The point where the wave crest meets the shoreline, the breaking point, races along the beach as the wave rolls in. If the wave approaches at a sufficiently small angle to the shore, this breaking point can travel along the beach faster than the wave itself moves through water. Surfers observe this routinely. But no water actually moves along the beach at that speed. The breaking point is a geometric intersection between the wave crest and the shoreline, sweeping laterally as the wave advances forward. No energy transfers along the beach through the breaking point. Phase velocity provides yet another example, and it is worth examining in some detail because it illustrates the information versus appearance distinction from a completely different direction. When electromagnetic waves enter certain materials, particularly at frequencies near absorption resonances, the crests of the wave can travel through the material at a speed exceeding c. This phase velocity represents how fast the wave pattern moves, the speed at which you would need to travel to stay on the same crest of the wave as it passes through the medium. At first glance, this seems like a clear violation of relativity. The wave crests are, after all, real oscillations of electric and magnetic fields. They carry energy. How can they exceed the speed of light? The resolution lies in the difference between phase velocity and group velocity. A single perfect sine wave extending infinitely in both directions carries no information because it looks the same everywhere. To send a message, you need to modulate the wave to create a pulse or a variation in the pattern that distinguishes one part of the wave from another. This modulation forms a wave packet, and the speed at which the envelope of the wave packet moves is the group velocity. The group velocity determines how fast information travels through the medium. In every known physical system, even when the phase velocity exceeds c, the signal velocity, which tracks how fast the leading edge of new information propagates through the medium, remains at or below c. The group velocity can also exceed c in regions of anomalous dispersion, but even then, no usable information outruns light. The individual wave crests may outrun light, but the overall pulse carrying the message cannot. The wave crests are patterns. The pulse is the information carrier. Patterns can exceed c. Information cannot. The distinction holds perfectly, even in a context that has nothing to do with shadows or projected dots. This is why physicists are so precise about what the speed of light actually restricts. It does not restrict the speed of appearances, projections, geometric intersections, or wave crests. It restricts the speed of causal signals, the rate at which one event can influence another event through the transfer of information or energy. Every apparent superluminal phenomenon ever observed, from quasar jets to laser dots to scissor intersection points to phase velocities, fails the information transfer test. None of them allow you to send a message faster than light. None of them create a causal shortcut between 2 points in spacetime. None of them violate the principle that the speed of light is, at its deepest level, the speed of causality. Every one of these examples, quasar jets, laser dots, scissors, ocean breakers, eclipse shadows, phase velocities, shares the same fundamental structure, an apparent motion that exceeds c, a reality in which no information, energy, or causal influence actually travels faster than light. The universe permits any number of illusions to race across the cosmos at absurd speeds, because illusions do not carry the causal connections that the speed of light governs. This is where the full picture of shadows and darkness comes into focus. A shadow sweeping across a surface at superluminal speed is not darkness traveling faster than light. It is a geometric pattern of photon absence playing out across a surface, where each point independently receives or fails to receive photons from a source via light-speed connections. The shadow has no physical substance to travel. It has no energy to carry. It has no information to transmit. It is the visual footprint of a changing geometric relationship between a source, an obstacle, and a surface. That relationship can evolve at any rate because it is not a physical entity subject to the speed limit on causal signals. Here is a thought experiment that drives this point home with particular force. Imagine a massive opaque disk positioned between a light source and a wall that stretches for 1 light second, roughly 186,000 miles. The disk casts a circular shadow on the wall. Now imagine yanking the disk sideways with incredible force, moving it rapidly across the light beam. The shadow on the wall sweeps sideways in response. If you move the disk fast enough, the shadow could cross the 1 light second wall in half a second, appearing to move at twice the speed of light. But trace the causal chain. The shadow at each point on the wall is determined by whether the disk blocks the light source, as seen from that point. The information about the disk's position propagates from the light source to each point on the wall via photons, at c. A given location on the wall is shadowed or illuminated based on whether the disk currently blocks its line of sight to the source, with that geometric information arriving via photons at light speed. An observer standing at one end of the wall cannot use the shadow's arrival at the other end to send a message faster than light. The shadow's position at the far end is determined by the disk's position relative to the light source, and the information about that position travels from the source region to the far end at c. The apparent superluminal sweep of the shadow does not create a causal shortcut between the two ends of the wall. This thought experiment also reveals something about the fundamental asymmetry between shadows and physical objects. If instead of a shadow, you tried to sweep an actual physical rod across the wall at superluminal speed, you would fail. The rod has mass. Accelerating mass to superluminal velocities requires infinite energy. The rod's atoms are connected by electromagnetic forces that propagate at c. If you push one end of the rod, the other end does not respond instantly. The push travels through the rod as a compression wave at the speed of sound in the material, far below c. The rod cannot be rigid at superluminal speeds because rigidity itself is limited by the speed of light. Even the concept of a perfectly rigid object is forbidden by relativity, because rigidity implies instantaneous communication between atoms, and instantaneous communication violates the causal speed limit. Shadows face none of these constraints because they have no mass, no internal structure, no forces holding them together. There are no atoms in a shadow connected by electromagnetic bonds. There is no compression wave propagating through a shadow's interior. A shadow is not an object, it is a pattern. And patterns are free. This freedom has been exploited in various astrophysical observations. When a pulsar, a rapidly rotating neutron star, sweeps its beam across a distant nebula, the illuminated spot can race across the nebula at superluminal apparent speeds. The dark region between successive sweeps moves just as fast. Astronomers have observed these superluminal sweeps and used them to study the geometry of pulsar beams and the distances to nebulae. The observations are routine, well understood, and completely consistent with special relativity. In some cases, astrophysical shadows can exhibit even more exotic apparent behavior. When an object passes between Earth and a distant light source, the shadow, or more precisely the penumbral region of reduced illumination, can sweep across Earth's surface at speeds determined by the geometry of the alignment. During certain occultations, the shadow geometry conspires to produce apparent speeds far exceeding c. Whether a given location on the ground falls in shadow depends solely on its own line of sight to the sun, and the aggregate pattern can race across the planet without any violation of causality. At this point, a natural question arises. If shadows can appear to move at any speed, and if shadows are just patterns of absent photons, then is there any useful sense in which darkness has a speed? The answer remains no, but the reason has become richer and more precise than when we started. Darkness has no speed, because speed is a property of things that travel, and darkness does not travel. The apparent speed of a shadow is a property of the geometric relationship between source, obstacle, and surface. It is not a property of darkness itself, any more than the speed of a movie character running across a screen is a property of light. The character is a pattern of changing illumination on a surface. The pattern has an apparent speed, but nothing physical, no substance called character, is running across the screen. Photons from the projector strike the screen vertically. The lateral motion is a geometric projection. This framework provides a complete and satisfying answer to the original question. If light has a speed, what about darkness? Light has a speed because light is a physical entity, a quantum of electromagnetic radiation that propagates through spacetime, carrying energy and information. Darkness has no speed because darkness is not a physical entity, it is a condition. Shadows can appear to move, sometimes faster than light, because apparent motion and physical motion are different things, governed by different rules. Physical motion is limited by c, apparent motion is not. And the reason for this difference lies in the deepest structure of the universe itself. The principle that the speed of light is really the speed of causality, the maximum rate at which one event can influence another across the fabric of space-time. This principle, and what it truly means for the architecture of reality, is where the story reaches its deepest and most surprising layer, because the speed of light governs far more than optics. It is the operating frequency of the universe. It is the speed at which causes connect to effects, the rate at which the cosmos stitches itself together moment by moment, and the reason existence has a coherent before and after it all. What darkness teaches us, through its utter inability to participate in this causal architecture, is just how extraordinary it is that anything in this universe moves, communicates, or connects at all. There is an equation carved into the bedrock of modern physics that most people have seen but few have truly absorbed. Einstein's field equations of general relativity describe how mass and energy curve the geometry of space-time, and buried within their structure is a constant that appears again and again like a heartbeat. The speed of light. It shows up not as a footnote about how fast photons happen to travel, but as a structural parameter that determines how space relates to time, how gravity propagates, how the universe holds itself together as a coherent sequence of events rather than dissolving into an unnavigable tangle of simultaneous everything. This is the insight that the question about darkness ultimately delivers. Not an answer about shadows or photons or the absence of particles, but a revelation about what the speed of light actually is. It is not merely the velocity of electromagnetic radiation, it is the speed of causality, the maximum rate at which any event anywhere in the universe can reach out and influence any other event anywhere else. The cosmic clock speed at which reality processes itself. To understand what this means, you need to see spacetime the way physicists see it, not as a stage on which events happen, but as a structure whose geometry dictates which events can influence which other events. This geometry was first described by Hermann Minkowski in 1908, 3 years after Einstein published special relativity. Minkowski realized that Einstein's equations were not just describing unusual behavior of moving clocks and shrinking rulers. They were describing a fundamentally new kind of geometry, a four-dimensional landscape in which space and time are woven together into a single unified fabric. Minkowski captured this insight in a statement that has become one of the most quoted lines in theoretical physics. He declared that henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. This was not poetry. It was mathematics. Space and time, which Newton had treated as absolute and independent backdrops for physical events, turned out to be different aspects of a single geometric entity. The separation between two events in space-time is not calculated the same way as distance in ordinary three-dimensional space. It follows a modified version of the Pythagorean theorem where spatial distances and temporal intervals contribute with opposite signs. This seemingly minor mathematical tweak has consequences that reshape the entire nature of reality. The most profound consequence is the light cone. From any event in space-time, you can draw a cone-shaped boundary that represents all the paths light could take radiating outward from that event. Picture a pebble dropped into a pond. Ripples spread outward in an expanding circle. Now add a vertical time axis rising upward from the moment of impact. The expanding circle at each successive moment traces out a cone shape in this three-dimensional picture of two-dimensional space plus time. That cone represents the boundary of the pebble's influence. Everything inside the cone, everything the ripples have reached, has been affected by the pebble. Everything outside the cone remains undisturbed. Light cones work the same way, but in 4 dimensions. From any event, light radiates outward in all 3 spatial directions at c. The boundary of this expanding sphere, plotted against time, forms a 4-dimensional cone. The interior of the cone, called the future light cone, encompasses every point in space-time that the original event can possibly influence. The exterior of the cone represents everywhere the event cannot reach, no matter what. This boundary is absolute. It does not depend on the observer's motion or position. Every physicist in the universe, regardless of their velocity, agrees on which events lie inside each other's light cones and which lie outside. The light cone is drawn by the speed of light, and this is where c reveals its true nature. The cone's slope, its opening angle in a space-time diagram, is determined entirely by c. If light travelled faster, the cones would be wider, allowing events to influence more distant regions in a given amount of time. If light travelled slower, the cones would be narrower, restricting causal influence to smaller regions. The specific value of c literally shapes the geometry of cause and effect across the entire universe. Inside your future light cone lies everything you can theoretically affect, every location you could send a message to, every object you could shine a flashlight on, every gravitational wave your mass could generate. All of it falls within this cone. Outside the cone lies everything that is causally disconnected from you at this moment. Regions so far away that even light, travelling since the instant of the event, has not had time to reach them. These regions are not merely hard to reach, they are structurally isolated from you by the geometry of space-time itself. No force, no signal, no mechanism of any kind can bridge the gap faster than c allows. The past light cone works the same way in reverse. It encompasses every event in the past that could have influenced you at this moment. The light arriving at your eyes from distant stars lies on your past light cone. The gravitational tug of the moon lies on your past light cone. Everything you can observe, measure, or be affected by falls within this backward-reaching cone. Everything outside it is unknowable, events that occurred too far away and too recently for their influence to have reached you yet. This structure is not a theoretical abstraction. It has measurable, observable consequences that physicists have confirmed through decades of experimentation and observation. When the sun produces a burst of radiation on its surface, Earth does not respond for 8 minutes and 20 seconds, the time it takes light to cross the 93 million mile gap. If the sun were to somehow vanish instantaneously, Earth would continue orbiting normally for those same 8 minutes and 20 seconds, because the gravitational information about the sun's disappearance propagates outward at sea. For those 8 minutes, Earth orbits a star that no longer exists, blissfully unaware because the causal signal has not arrived. This is not hypothetical extrapolation. It follows directly from general relativity, which describes gravity not as an instantaneous force reaching across space, but as curvature in spacetime that propagates at sea. Newton's formulation of gravity implied instantaneous action at a distance, a feature that troubled Newton himself. Einstein resolved the problem by showing that gravitational effects travel at the same speed as light. Changes in the gravitational field ripple outward from their source at sea, just like changes in the electromagnetic field. The confirmation came spectacularly in 2017, when astronomers detected gravitational waves and electromagnetic radiation from the same event. A neutron-star merger, approximately 130 million light-years away, catalogued as GW170817. The gravitational waves, ripples in the fabric of space-time produced by the violent collision of two ultra-dense stellar remnants, arrived at Earth's detectors within 1.7 seconds of the gamma rays from the same event. Both signals had travelled for 130 million years across the cosmos. Their near-simultaneous arrival confirmed that gravity and light propagate at the same speed to within 1 part in a million billion. Causality, whether transmitted by photons or by space-time ripples, travels at the same universal speed. This observation carried enormous significance. For decades, physicists had assumed that gravitational waves travelled at sea based on the mathematics of general relativity. But assumption is not confirmation. The neutron-star merger provided the first direct measurement, and the result was unambiguous. The universe has one speed of causality, not two, not several, one. Whether the messenger is a photon, a gravitational wave, or any other physical carrier of information, the maximum delivery speed is c. Now bring this framework back to the question of darkness. The reason darkness has no speed is not merely because it lacks physical substance, though that is true. The deeper reason is that darkness has no place in the causal structure of spacetime. The light cone framework describes how events influence other events through the propagation of physical signals. Photons, gravitational waves, particles carrying forces. Darkness is not a signal. It is not an event. It does not appear on any spacetime diagram as a point that emits causal influence. There is no light cone emanating from darkness, because darkness is not a thing that happens. When a region of space becomes dark, the causal explanation always traces back to an event involving light. The source turned off. An obstacle blocked the photon path. A star collapsed. These are the events, the causes. The darkness at the observation point is the effect, the consequence of photons ceasing to arrive, and the causal connection between the triggering event and the resulting darkness propagates at sea, carried by the final photons in transit or, equivalently, limited by the speed at which information about the source's state can reach the observer. A shadow sweeping across a surface at apparent superluminal speed does not create a new light cone connecting points along the shadow's path. Each point on the surface has its own independent causal connection to the light source, through the photons that either arrive or fail to arrive at sea. The shadow is not a causal chain. It is a pattern of independent responses to a changing geometric configuration, and patterns do not create causal connections. This is why the entire framework of speed, velocity, and propagation simply does not apply to darkness. These concepts belong to entities that participate in the causal structure of space-time, entities that carry energy, information, or physical influence from one event to another. Darkness participates in none of this. It sits outside the causal framework entirely, which is exactly what you would expect from something that is not a thing. The consequences of c being the speed of causality extend far beyond optics and shadows. They reshape our understanding of the cosmos at every scale, from quantum mechanics to the large-scale structure of the universe. At the quantum level, entangled particles exhibit correlations that appear to transcend spatial separation. Measure the spin of one entangled electron, and the other electron, no matter how far away, instantly assumes a complementary spin state. This correlation is real and has been confirmed in numerous experiments, most famously in tests of Bell's inequalities that rule out local hidden variable explanations. Einstein himself was troubled by this phenomenon, calling it spooky action at a distance in a letter to Max Born. The effect appears instantaneous, seemingly violating the causal speed limit. But careful analysis reveals that no usable information transfers between the two particles. You cannot control which outcome your measurement produces, so you cannot encode a message in the result. The distant particle's state correlates with yours, but you cannot exploit that correlation to send a signal faster than light. To extract any meaning from the correlation, you need to compare the two measurement results, and that comparison requires a conventional communication channel, one that operates at or below c. The entanglement creates a correlation without creating a communication channel. Causality remains intact. The speed of light as the speed of information transfer is preserved even in the bizarre domain of quantum mechanics. This is one of the most subtle and frequently misunderstood results in modern physics. Quantum entanglement is real. The correlations are stronger than any classical mechanism can explain. But the no communication theorem, proved rigorously within quantum mechanics, demonstrates that entanglement cannot be used to transmit information faster than light. The causal speed limit survives the quantum revolution unscathed. At the cosmic level, the finite speed of causality creates the observable universe, a sphere of space from which light has had time to reach Earth since the cosmos began. The radius of this sphere is approximately 46.5 billion light-years, larger than the 13.8 billion light-years you might expect from the age of the universe, because space itself has been expanding throughout cosmic history. Objects that emitted light 13.8 billion years ago, when the universe was young and small, have since been carried to much greater distances by the stretching of space. The light has arrived, but the sources have receded far beyond where they were when they emitted it. Beyond this observable sphere lies space that almost certainly exists, but from which no signal, no photon, no gravitational wave has had time to reach us. These regions are causally disconnected from our location. They might as well exist in a separate universe for all the influence they can exert on us or we on them. The observable universe is not a physical boundary. It is a causal one, drawn by c and the finite age of the cosmos. The expansion of space adds another dimension to this causal isolation. Distant galaxies recede from us at speeds proportional to their distance, carried by the expansion of the space between us. Beyond a threshold distance known as the Hubble radius, roughly 14 billion light-years, the recession velocity exceeds c. Galaxies beyond this distance are carried away faster than light can bridge the gap. We can observe some of them, because their light began its journey when they were closer, but we can never send a signal that will reach them. They have crossed permanently beyond our causal horizon. The speed of light, combined with the expansion of space, draws a boundary around our sphere of possible influence that shrinks with every passing moment as dark energy accelerates the cosmic expansion. This shrinking sphere of causal contact creates a future that is both predictable and haunting. In roughly 100 billion years, the accelerating expansion will have carried virtually every galaxy beyond our observable horizon. The cosmic landscape will have undergone a transformation so complete that future astronomers will inhabit an entirely different scientific universe than the one we study today. Consider what that future looks like in detail. The Milky Way and Andromeda will have long since merged into the elliptical galaxy, sometimes called Milkomeda. The other members of the local group, the small collection of gravitationally bound galaxies in our immediate neighborhood, will have been absorbed into this merged system, or will orbit as minor satellites. Beyond Milkomeda, the sky will be empty. Not just sparse, empty. Every galaxy beyond the local group will have been carried past the cosmic horizon by accelerating expansion. Their light, stretched to wavelengths longer than the observable universe itself, will be undetectable by any conceivable instrument. The cosmic microwave background, that ancient glow from the Big Bang that currently fills the sky with detectable radiation at a temperature of 2.7 Kelvin, will have redshifted into oblivion. Its photons, stretched by trillions of years of cosmic expansion, will carry wavelengths so long and energies so low that they will be indistinguishable from the quantum vacuum itself. The single most important piece of evidence for the Big Bang will have been erased from the sky. Future astronomers in Milkomeda will look outward and see nothing. No distant galaxies, no cosmic microwave background, no evidence that the universe was ever different from what they observe. They might develop sophisticated physics, they might build powerful telescopes, they might achieve scientific capabilities far exceeding our own, but they will lack something we currently take for granted: the causal connections to distant cosmic regions that make modern cosmology possible. These future scientists might conclude that their galaxy constitutes the entire universe, a single island of stars floating in an infinite, static, empty void. They would have no way to discover cosmic expansion because there would be no distant galaxies to observe receding. They would have no way to infer the Big Bang because the evidence would have been stretched beyond detection. They would have no way to measure dark energy because there would be no cosmic structure to reveal its effects. Their cosmology would be completely wrong, not through any failure of intelligence or methodology, but because the universe would have pulled the evidence beyond their light cones. This scenario is not speculative fiction. It follows directly from confirmed observations of cosmic acceleration combined with the finite speed of causality. The universe is actively erasing its own history, carrying the evidence of its origins beyond the causal horizons of future observers. We happen to live during a cosmological golden age, when the evidence is still accessible, when distant galaxies are still visible, when the cosmic microwave background still glows detectably across the sky. This window will not last forever. The universe has an expiration date on its own observability, and the timer is set by the speed of light. This is the deepest reason why the question about the speed of darkness matters. It is not really a question about darkness at all. It is a question about the infrastructure of knowledge itself. The speed of light determines not just how fast photons move, but what can be known, what can be communicated, and what can be influenced across the fabric of space-time. Every measurement, every observation, every act of communication in the entire history of every civilization that has ever existed or will ever exist is bounded by c. The speed of light is the bandwidth of reality. Darkness has no relationship to this bandwidth because it carries no data. When a region goes dark, information has not arrived, a message has not been delivered, a connection has not been made. Darkness is the absence of connection, the default state of a universe in which causal links must be actively established through the exchange of physical signals travelling at finite speed. In a cosmos where information propagation requires physical carriers obeying a speed limit, the baseline condition is not illumination. It is darkness. Light is the exception, the active effort, the causal handshake between distant regions of space-time. Darkness is what the universe looks like when no handshake is underway. This realization inverts the intuitive relationship between light and dark. Human experience treats light as the ordinary condition and darkness as something that must be explained. Why is it dark at night? Why are there shadows? Why can we not see in the void between stars? But from the perspective of physics, the question runs the other direction. The universe is overwhelmingly dark. The space between stars, the space between galaxies, the vast cosmic voids that make up roughly 80% of the observable universe by volume, nearly all of it is dark. Photons are rare messengers travelling through an ocean of emptiness. The question is not why darkness exists. Darkness is the default, the ground state, the canvas. The question is how light manages to connect anything at all across such incomprehensible distances. This inverted perspective connects to one of the oldest and most beautiful questions in cosmology, Olbers' paradox. In 1823, the German astronomer Heinrich Olbers formalized a puzzle that had troubled thinkers for centuries. If the universe is infinite, eternal, and filled with stars, then every line of sight in every direction should eventually terminate on the surface of a star. The night sky should be blazingly bright, every point as luminous as the surface of the sun, because no matter where you look, a star should be there at some distance. The night sky is obviously not blazingly bright, it is dark. Olbers' paradox asks why. The modern resolution involves several factors, but the most fundamental one is precisely what we have been discussing: the finite speed of light combined with the finite age of the universe. The cosmos is approximately 13.8 billion years old. Light has been travelling for at most 13.8 billion years since the universe became transparent, so stars beyond a certain comoving distance, currently about 46.5 billion light-years due to expansion, remain invisible to us. We cannot see them. They are beyond our past light cone. The night sky is dark because the universe has a finite age and light has a finite speed, which means there is a maximum distance from which starlight can have reached us. Beyond that distance, the universe is causally silent, dark, not because it is empty, but because its light has not yet arrived and, in many cases due to accelerating expansion, never will. The darkness of the night sky is therefore not a trivial observation. It is direct evidence for the finite speed of causality and the finite age of the cosmos. Every dark patch between the stars is a window into the causal structure of spacetime, a region where the light cones of distant sources have not yet intersected with your location. The darkness you see is the geometry of cause and effect made visible, or rather, made invisible. The answer, of course, is that light connects things because the universe permits it, up to a limit. That limit is c, and the existence of that limit is what gives the universe its structure. Without a finite speed of causality, every event would influence every other event instantaneously, regardless of distance. There would be no meaningful separation between here and there, between now and then. The past could affect the future, and the future could affect the past simultaneously. The concept of sequence, of before and after, of cause and effect would dissolve. The universe would not evolve. It would simply be, all at once, every event tangled with every other event in an incoherent web of mutual instantaneous influence. The finite speed of light prevents this. It enforces an order. Event A can influence event B only after a time interval determined by the distance between them and the speed c. This creates a temporal structure, a sequence, a directionality to how events unfold. Causes precede effects. Signals arrive after they are sent. The universe has a history because information takes time to travel, and it takes time to travel because c is finite. The arrow of time, the narrative of cosmic evolution from the Big Bang through star formation and galaxy assembly to the emergence of life and consciousness, all of it depends on the finite speed of causality maintaining the coherence of events across space and time. Darkness plays no role in this narrative because it is not a participant. It does not carry signals. It does not enforce order. It does not connect events or maintain coherence. It is the canvas on which causal connections are drawn, the silence between the notes of a cosmic symphony played at the tempo set by C. And yet, paradoxically, thinking carefully about darkness reveals the symphony itself more clearly than almost any other topic in physics. The original question, if light has a speed, does darkness, carries within it an assumption so deeply embedded in human cognition that most people never even notice it. The assumption is that light and dark are symmetric, that they are equal and opposite, that if one has a property, the other should have a corresponding property. Speed for speed, wavelength for wavelength, entity for entity. Physics demolishes this symmetry completely. Light is a physical phenomenon described by quantum electrodynamics, the most precisely tested theory in the history of science. Its properties are predicted and confirmed to 12 decimal places of accuracy. It mediates the electromagnetic force, one of the 4 fundamental interactions in nature. It is emitted and absorbed by charged particles. It carries energy, momentum, angular momentum, and information. It curves space-time through its energy content. It creates measurable pressure on surfaces it strikes. It has a quantum nature, existing as discrete packets called photons, each carrying energy proportional to frequency, as described by the Planck relation. It exhibits wave-particle duality, behaving as waves in interference experiments and as particles in photoelectric detection. It obeys Maxwell's equations classically, and the rules of quantum field theory at the fundamental level. Darkness has none of these properties. Not a reduced version of them, not a complementary set, none, zero. Darkness is the absence of the phenomenon that possesses all of these properties. The asymmetry is total and complete. Light and dark are not 2 sides of a coin. They are a coin and empty space where a coin could be. They are not yin and yang, equal forces in cosmic balance. They are a thing and the lack of that thing. Asking whether darkness has a speed is exactly as meaningful as asking whether the hole in a wall has a colour, or whether the silence in a concert hall has a key signature, or whether the gap between 2 books on a shelf has an author. And yet, that flawed assumption, the intuition that light and dark must be symmetric, is not stupid. It is not a failure of intelligence. It is a product of 3.5 billion years of biological evolution, on a planet where the day-night cycle was among the most critical environmental variables any organism faced. The alternation between light and dark governed when to hunt and when to hide, when to forage and when to sleep, when predators could see you and when you might escape their notice. Creatures that treated darkness as real, as dangerous, as a thing to be navigated and feared and respected, survived at higher rates than those that dismissed it as a mere absence. Evolution does not optimize for physical accuracy. It optimizes for survival. And for survival, darkness absolutely is a thing, a condition requiring heightened vigilance, altered behavior, different strategies for finding food and avoiding predators. The human brain carries this evolutionary legacy into every physics classroom and every late-night conversation about the nature of reality. When someone asks whether darkness has a speed, they are not asking a foolish question. They are asking a question that reveals the gap between evolved intuition and physical truth. That gap is one of the most interesting features of human cognition, and bridging it is one of the great achievements of scientific thinking. Science is, in many ways, the systematic discipline of overriding intuition when evidence demands it. Darkness having no speed is a small example. Quantum mechanics, general relativity, and cosmology are filled with larger ones. But the pattern is always the same. Reality operates differently from how evolution trained us to expect, and discovering those differences is the beating heart of physics. Physics does not diminish the human experience of darkness by revealing it to be an absence. If anything, it enriches it. Knowing that every dark sky, every shadow, every unlit room represents a region where the universe's most extraordinary messenger, the photon, is not present, transforms the experience of darkness from something mundane into something charged with meaning. The darkness between stars is not empty in a boring sense. It is empty in a profound sense, a vast ocean of causal disconnection through which rare photons carry the only links between island civilizations of matter, separated by light years of silence. Each photon crossing that void is a thread in the causal fabric of spacetime, a connection between 2 points that would otherwise be as isolated from each other as if they existed in different universes. The darkness beyond the observable universe is not merely unexplored space. It is a region structurally severed from our causal history, a place from which no information has ever reached us, and, if cosmic expansion continues accelerating, no information ever will. That darkness is not a substance filling the void beyond our cosmic horizon. It is the absence of causal connection itself, the ultimate expression of what it means for the speed of light to be finite in a universe of potentially infinite extent. The next time you stand outside on a clear night and look up at the stars, consider what you are actually seeing. Each point of light is a causal connection, a stream of photons linking your retina to a nuclear furnace burning years or centuries or millennia away. Each photon began its journey at the moment of its creation, travelling at exactly c, carrying a quantum of energy and a fragment of information about the star that made it. That photon crossed the void between stars, a void containing no matter, no light, no causal connections of any kind, and arrived at your eye to complete a link between 2 points in space-time that would otherwise have no knowledge of each other's existence. Now look at the dark spaces between those stars. Those gaps are not filled with a substance called darkness. They are regions where no such causal link exists at this moment. No photon connects your eye to those directions right now. No information flows, no energy arrives. No event in those dark regions is currently influencing any event at your location. The darkness is the absence of connection, the default state of a universe where connections must be actively forged by physical messengers obeying a finite speed limit. Imagine for a moment a universe without that speed limit, a universe where causality was instantaneous. In such a cosmos, every event would instantly influence every other event everywhere. Stars would not appear as points of light arriving from the past. They would simply be their current state simultaneously present to every observer in the universe. There would be no delay, no travel time, no past light cone containing old information. There would be no observable horizon, because information from every corner of the universe would arrive simultaneously. There would be no darkness between stars, because the photons would not need to travel. They would simply be everywhere at once. But such a universe could not have history. Without travel time, there is no sequence. Without sequence, there is no evolution. Without evolution, there are no stars being born and dying, no planets forming, no chemistry building toward complexity, no life emerging from inanimate matter. The finite speed of light is not a limitation on the universe. It is the mechanism by which the universe creates time, history, and change. It is the reason the cosmos has a narrative rather than a single frozen state. The delay introduced by c, the time it takes signals to cross distances, is what allows the universe to be different at different places and different times. It is what makes locality meaningful. It is what makes the universe interesting. Darkness is the visible sign of that delay. The dark gaps between stars are the temporal spaces where light has not yet bridged the gap, or where no light was sent in the first place. The dark sky behind the cosmic microwave background is the temporal space before the universe became transparent, a time so early that no photons survive from it in any detectable form. The dark future that will eventually engulf distant galaxies as they recede beyond our horizon is the temporal space that cosmic expansion is creating faster than light can fill. If light has a speed, does darkness? The question dissolves once you see it clearly. Light has a speed because light is a physical entity that participates in the causal structure of spacetime. Darkness has no speed because it is not an entity and does not participate. The speed of light is not just a number describing how fast photons travel. It is the architectural constant of reality, the parameter that determines the geometry of cause and effect, the value that separates what can influence what from what remains forever isolated. Everything in physics, from quantum mechanics to general relativity to cosmology, is built on this foundation. Darkness is the condition that remains when that foundation has no signals to carry. It is the resting state, the blank page, the cosmic default, and the fact that light exists at all, that photons bridge the unimaginable distances between stars and galaxies and clusters, carrying energy and information at the precise speed the vacuum demands, is not the ordinary part of the story. It is the extraordinary part. Light is the miracle, the active process, the universe reaching across the void to touch itself and know itself, through the exchange of massless particles travelling at the one speed reality allows. Darkness is just what was already there, the silence before the music, the stillness before the wave, the void before the connection. In a universe that communicates at the speed of causality and falls silent everywhere else, darkness is not the mystery, light is. And the speed at which light travels, the speed that governs information, causality, and the very structure of space-time, is the deepest answer physics has ever found to the question of why reality works the way it does, not because it tells us something about photons, but because it tells us something about everything.